All right, Mr. Greg Everett, we're looking at some milling uh, discrepancies is the word I think I want to use, but they're worse than that. Milling problems, milling headaches, uh,
Nightmare.
nightmares, right? If as a technician or a clinician, you see this surface finish come out of the mill, maybe you think, all right, well, this is normal. I got to grab my handpiece and dial things in. But I
Yeah.
know what you're here to talk about today is this is not normal, or this should not be what you're happy with. Tell us, what are we looking at here, and can we solve this, and how good can we make things?
So this is one of a few common surface defects that you can get when you're milling your own units. Um, and Yeah, we wanted to go through a few of them and kind of give you guys a bit of a walkthrough to see what kind of common causes and solutions there are to nasty crowns like this.
Yeah, I mean, I see some weird striations and like ledges, and oh man, I mean obviously for many labs these surface finishes would be rejected, and then you'd be getting a call or someone would be troubleshooting their machine. So what are the common issues, like these images? What problems do these represent, and what are we going to talk about here today?
Well, 10,000-foot view, this represents waste in your business because,
Yes.
I mean, really, because if you walk into any lab, it's kind of like a joke, like the make it work. Everybody just makes it work, and then they say it is what it is. So a technician will take this and he'll spend an hour hand forming it with a handpiece to try to make it work. And that's just not acceptable in this day and age with precise technology. Um, yeah, that's kind of top down view.
And I imagine this is not how a mill performs out of the box. My guess is it starts subtle and then it
Yeah.
just slowly gets worse and worse over time, to where all of a sudden you're like, is this where we started a year
Hmm.
ago or 6 months ago, whenever? And maybe it's like the frog in a pot type of analogy, where it just
That's
slowly gets
exactly what
bad
it is. Yeah.
to the point where the lab owner or someone comes along and goes, what the hell is this?
Yeah, yeah. And the majority of the images that I have to show you guys today are actually from our customers. And one of the things I wanted to kind of achieve in doing this is to help people understand the different flavors of bad mill jobs, because we'll get a call, I'll get a call saying, hey, the mill it's making lines, or it's not good. And so that fires off a troubleshooting process where we, look at the images, and then we'll say, oh, you've got, X type of, surface defect. And those surface defects map to different solutions. So and I don't see anybody talking about this stuff out there. So I thought it was a good opportunity to do a little bit of, I guess, outreach.
Yeah, we are for sure starting with the problem here today, and I can't wait to talk about the solution. A quick intro. I'm Rob Laizure. This is Greg Everett. Greg, how many years have you been focused on optimizing milling machines?
Oh man, I was in a lab for a decade and messing around with that constant. So it's kind of been I would say I've been focused on making better and acceptable crowns off of machines for my entire dental career. So oh geez, I got in at '07. It's been a few years.
Wow, we're almost to the 20-year mark.
Dude,
I
how did that
love it.
happen?
All right.
Yeah.
And how many milling machines have you rebuilt or repaired or serviced in your
So
career?
so in our like company, it's called Denteon, and we're in year 4, and we've closed over about close to 700 tickets now. So
Wow.
that ranges from a full rebuild to a just help them on the phone, but it's stacking, man.
I was just, before we jump in, a curious question. How often can you talk to someone on the phone to solve one of these issues so that they don't have to box up their machine and send it to you and go, they're out of production for however long it takes? Like, how far can you go with phone support to help someone remotely with some of these issues?
We go as far as they're willing to go, because that's the optimal solution, is to help the lab tech or the lab owner help themselves, or the clinician. We have a lot of customers that are clinicians now, and it can go. If they're communicative and willing to do some testing, um, then we can oftentimes get to a root cause and a solution remotely. Um, Root cause is like majority. We're probably figuring out what's wrong with it by 80-90% of the cases that happens remotely. Um, and then solution, we'll ship you parts and a screwdriver and walk you through doing it yourself, or you can ship the machine here. We do it. And so I,
So
we definitely go towards remote a lot heavier.
a little bit of a choose your own adventure, right? If I
Yeah,
have a little MacGyver in me and Greg's gonna be with me on FaceTime to help me screw the things in the right spot, then we could do it remote. I love that.
yeah,
So,
yeah,
Greg, outline what are the problems we're
yeah.
going to address today?
Okay, so there are kind of a lot of them, but I've narrowed them down to a handful of different sort of defects that come in, um, and they're somewhat organized in order of commonality. Like, this is by far the most common one we get. Um, Followed by offset lines, chatter, and then lines through finish, gouging, and then equator line. There are some corner cases that aren't here, but this is definitely going to hit the majority.
So, with this smorgasbord of an image here in the backdrop, what could you just visually tell us? Like, what's the terminology for these issues that we're looking at here?
So what we're looking at here is my collage for chatter, and we'll
Okay,
and we'll jump back into it. But what I've done is I've prepared a paint image of each one of
love
these,
this.
so that I can kind of walk you through, define it, and then give you guys like a bullet point solve or root cause. Um,
All right, let's jump
so
in. What do we got here?
I will guarantee within absolutely 100,000% chance that everybody who mills zirconia has chipped a margin.
Yep.
And so, but what we need to, so we get an image that's, similar to this. I'm going to go bigger here. Something like this. So this is like classic margin chipping.
Can you zoom in? Oh, we just lost the image.
There we go.
Control Z.
Yeah, there we go.
There we go. Yeah, perfect.
So yeah, this is, you've got a thin ceramic, shape, and it's just sloughing off. It's getting like sawtooth, here and there, and further on. Um, and so this is a margin chip, and this is really really quite common. And then there's this type of thing, which is kind of beyond the chip. This is trauma. This is an impact. So
That's a tool
yeah,
crashing type of
yep, that's
thing.
that's a collision. So the non-cutting portion of a tool hit the side of the crown, and it blew it out. Um, and so after seeing so many of these, get to the point to where it's like I get the image, read the tea leaves, and be like, all right, we know where we're going with this one.
I have a little margin chipping, Greg, and you see the image, you're like, well, you have more than a margin chipping. You've got trauma.
Yep, 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 exactly. So because the vast majority of margin chipping is like this, let me hit a couple of the high points on that. So first off, zirconia. We're machining zirconia. Zirconia doesn't want to be machined. It's kind of a nasty material to cut, um, and especially when it gets thin, it wants to chip. And so the number one thing that we always ask the customer is, what is your margin line offset? So if you take, and this is in the design. So if you have
And
a
it's the that's a 3-shape term is margin, line, offset, and then
Yeah,
the ExoCAD term is crown
yeah,
border.
yeah. It's something along those lines. Someday I'm going to figure out how to draw a better crown here. Um, Here we're going to do. This is the offset. That's like your. This is a cross section, and this is the inside of the crown. And what
Yep.
you've got is the software is going to expand the margin
Yep.
by a value so that it's thicker so that it can be machine successful. And what we like to see, the safest value is 0.2. So that's 200 microns. That's the absolute safest, and I believe that's default in 3-shape. Um, I'd have to ask an ExoCAD guy what default in ExoCAD is. And then as you go lower, so if we're at 150, this is still stable. And if we go down to like 0.08, like 80, we're starting to get unstable. And now we're going to start to chip a percentage of our units at this stage. And why would you want to make this less? Every single customer, every single lab tech wants the margin as thin as possible because it means
Yeah,
less handwork.
if you got a feather edge or a light chamfer, you're going to add that thickness, and then the emergence of the crown from the natural tooth to the crown junction right there, and there's going to be a bulge, a bump,
Yeah.
and then now we want to finish that down. But if we try to finish it to 0.08 in the mill, we now have risk of chipping.
Yep. So
But if we go ahead.
the lower the value, the higher the risk of chipping.
And the lower the value, the faster the finishing. So there's this
Yeah.
tension.
It's
Yeah.
a trade-off. Yeah, yeah. And so if a mill isn't tight or if your tools aren't right, that rhymes, um, then you will not be able to achieve this successfully. Um, and so, we get a call, we're getting chip margins. I'm going to ask what that offset's set at. And like in this example, I can tell visually that the offset is too low. There's no offset.
There's
It's
almost
like,
no
yeah,
offset. Yeah.
yeah. It's like a knife edge. So that is the underlying cause of this chip.
So that's the tool attempting to finish like a blade surface, right? Like this ultra point. And because of that, whether it is it just vibration or whatever, and it's just chipping away the margin as it goes.
Yep, yep. So when we're cutting zirconia, oh, too many control Z's. Okay, so when we're cutting zirconia, we have a burr or tool, whichever term you like, and it's gonna have one cutting edge, so it's going this way, and this is a cutting edge. This is a cutting edge.
We're looking at a cross section of the flutes, right?
Yeah, this is the tip of the tool if you're gun sighting down. Okay.
Right.
And so we're rotating around this way, and this cutting edge is cutting, and this cutting edge is cutting. And when we're engaged with the material, it's an interrupted process. So only one cutting edge is loaded at a time, usually. And so that interrupted process makes vibration. So you have, yeah, it's actually more of a square wave like this. So you're on, off, or on, off, on, off, on, off, and that makes a ton of vibration. And vibration and thin ceramics don't mix inherently.
Well, and what about like cheap zirconias or like cheaper zirconias more prone to chipping versus premium zirconias that have smaller particles and maybe higher density? Is there any type of relationship there?
There's actually an immense relationship there. So, if you can imagine, if you get yourself in the POV of that tool and like zoom in by like 2000x, we're cleaving the material with that cutting edge. And if you have, bigger chunks, they have to get kind of pushed out of the way. They don't want to readily fracture. So let me try to draw you like this is I don't know, really, really crappy electron microscope image of the particle size of zirconia. If I try to cut this guy has to just move out of the way, and we're going to create a fracture line right there, right? And so a big chunk is problematic. But if we have a lot of little chunks and then we cut it, you have much higher tendency for it to separate with less energy. And so small particle size, big win. If your zirconia has like inclusions or voids, like say you've got particles, but in between those particles there's a void, it'll also cut rougher. And really a lot of the zirconias out there are big particle, big void, because they're made with binders, and then the binders are burned out, and after the binders burned out, you leave a void, and it's as simple as that. So yeah, the material drives the process highly.
Obviously, it's a combination of lots of things, right? Dialed in mill, good tools, good zirconia. On the topic of zirconia, what zirconias are at the top of your list that you like to mill?
So it's I tell people to look at the way their zirconia is made and ask questions, because there's two methods that are used out there right now. There's a mechanical press, so that can be isostatic or it can be done like axially, and that's where you got a binder and you're squishing the material together to make the block. And then you've got the colloidal process, which is much rarer, but it's far superior, because we get way better densification, and it requires a smaller particle size to work. And so I tell people to shop for colloidal process zirconia, because it machines the best. And if you start shopping around for that, you're going to be led to the best one that's out there, which is the Harvest stuff. And so to answer your question, I'm a Harvest zirconia guy. I got them sitting right here,
Wonderful.
man.
Yeah.
The green band.
The green ring, I'm familiar with it. That's what Rebel 3D is using for all of our Rebel crowns, and we've
Yeah,
made that choice intentionally. It's a great margin line and all that, but we'll do an episode on the Rebel crown later, Greg, and
we should.
some of the fun stuff we're doing there.
I
All right,
think
let's.
you've got to control me, Rob, because I will go on a tangent.
No,
Uh,
this is fascinating. So chipped
okay.
margins. Back to our topic here in this
Yeah,
slide.
yeah. So we cover marginal line offset, and then the other and cover material, and then the other thing is tooling. And so we want a sharp tool, and we want
For sure.
a good tool in good shape. And I got to come up with a better metaphor. But the way that I explain this to people is, imagine you have a block of cheddar cheese and I have a steak knife. If you cut it with a nice sharp steak knife, it's clean, it peels, and it's nice, and you got a clean surface. Now shove the handle of the steak knife through the cheese.
It will cut
You,
it.
you can cut it. You can cut it, absolutely. But you're gonna traumatize it. You're gonna micro fracture it. Well, in a cheese, I guess that'd be a macro fracture. But
Yes.
so a dull tool or a kind of garbage, super cheap, import tool, they're the steak knife handle. And a high-end tool that has been engineered for the application, is the sharp, fresh, Japanese steak knife. Um,
Love it.
and we want that sharp edge. We want that because the sharper edge means less energy in the cut, which means less trauma to the material and way less chipping. In fact, tooling is a through line through this entire conversation. Better tooling solves a lot of this stuff. Yeah, and I'll try to stay kind of on topic. Yeah.
Anything more to say about chipped margins? So
Um,
we know what it is, right? The
yeah.
trauma. So maybe the design file didn't have the margin line offset. Could be an issue. Could be the tool. So what types of things are you going to do to troubleshoot and fix this problem?
So we're gonna look at. I'm gonna ask them what tools are you using, what zirconia are you using, what's your maintenance like on the machine. That's a contributing factor. And then we're gonna look at software to make sure they run in the right strategies and stuff, because these collisions happen because of the software. It doesn't know the shape of the tool, and so it runs it into stuff. And that's a pretty common thing to run into. So yeah, we probably could move into the next one.
Let's do it.
Yeah, and keep the show on the road here. So let's look at offset lines. So this one is a machine issue, 100%. It's not
not
software.
a zirconia collar?
Nope, nope. It's it's your machine's out of whack if you're getting this. Um, and to define an offset line, we have a crown, and when the machine flips to mill one side versus the other, it's skewing them because it's not hitting the same point in space when it flips that it started on. And so what you end up with is a crown that's notably shifted. So like this one here, for instance, the top of the crown, and we're only looking at this defect, not this. The top of the crown is shifted, and this is shifted like a buckle or like a distal mesially, and it's occurring when the machine flips. This is super duper common, and it has to do with calibration, mechanical wear, and is the disc flopping around inside the machine. Sometimes the machine's not holding the disc right, and it's got motion, and it can move during the milling, and you end up with this. So yeah, that's this one we see. This is a big part of what we see. Right below margin chipping.
What do you call this again? The
offset lines. Yeah,
offset lines.
line.
Yeah.
I should probably label these.
Yeah. So the you have a solid geometry in space, and you're going to mill one side, flip it, mill the other, and your machine's out of whack, and so it's just not aligning. It's like milling two bowls to form a basketball, but the bowls
that's exactly it. Yep.
The bowls are, Greg, I'm not a smart man, but sometimes I get lucky. Got it.
Yeah, definitely. Yeah, so this is offset lines, and you can see it in my file name up there. So that one's pretty quick. This one's a call your support. If you see this, don't fuss around with it. You can start by trying to calibrate the machine, but if it still happens after you calibrate the machine, then you're doing a support ticket. And that's pretty much where that one's going to go. So now we'll shift gears up into the one I started with, which is chatter. Chatter, that's a term I've actually stolen from industrial machining, because this is a common defect in a machine shop. And you know how we were talking a minute ago about the vibration that can occur because we're milling and it's an interrupted process. It's high speed, it's at 30,000 RPM, but it's still on off. And so if you have anything in your machine that is not rigid and has play, it'll allow those natural vibrations to like propagate and get excited and create like resonant frequencies. And you'll get this when that's happening.
So it's this idea that vibration at some level is always occurring, but then if your machine is loose, it allows the vibration to cause this movement that then manifests as this chatter.
Yeah. So it's the job of a milling machine to be rigid and to resist the vibration. That's why whenever people ask me like what kind of stuff I like in milling machines, I say rigidity and horsepower. Those two things. Most important things. Horsepower lets us go fast. So if you think about yourself as a tool and wanting to vibrate, and the machine's not resisting that, so we're going to be in the cut, and it's going to make a cut, and then it's going to bounce out, and then it's going to revert and bounce out and bounce out and bounce out. And then you create this sort of a surface because the tool is not cutting, it's bouncing. And then it's
perfect sense.
Yep. And then especially like, so this image here, it's very apparent because they're almost perfectly vertical. They're aligned with the axis of the tool. And so you're just seeing ripples from the vibration.
So every time it goes to apply pressure and then it's like releasing, and then it's this dramatic vibration effect to where if a machine was very rigid, and draw the red line again, that would be the machine that you just dialed in and dramatically increased the rigidity. I'm sure there's a little bit of vibration, but then it maybe just goes unnoticeable.
So this is what we have in the image, and then I would say, a rigid machine is probably, it's there, but it's dampened by the rigidity. And that's why if you go to look at industrial machines, they're all thousands and thousands of pounds. They're built out of giant castings because you have to dampen the vibrations.
And dampening, you mean like absorbing or resisting the vibrations?
Absorb and resist. So like, Rob, have you ever driven in a really clapped out, crappy car that had blown out shocks? Like,
no, but I've had a wobbly front end where the steering wheel shakes.
Okay, yeah. I mean, so same kind of idea. You go over railroad tracks in a car that is, been highly abused and the shocks are blown out. It's going to hit that bump and then bounce a few times before it settles out. But if you have good shocks, the shocks dampen the vibration. They absorb it. That's why they call it a shock absorber. And then your ride is smooth. So rigidity and mass are doing the same thing in a milling machine. They're absorbing the vibration.
And a lot of dental mills don't have a ton of like weight or mass to them.
That's true.
So yeah, because how do we solve that?
We have market pressures that have wanted, people want machines that are sub 30K, which is great because it allows access to technology, and they need to be lightweight so they can go on a bench top. So right. those two things are in direct conflict with like the ultimate milling machine. So what do you do to get the best of both worlds? It's a balance of material, tool, milling strategy, and the machine being as tight as it can be reasonably. So chatter can be tuned out. So let's say that if I was getting this on a machine, it is possible in a lot of cases to tune the milling strategy so that we don't get the machine excited vibrationally, and we get a way better surface finish with just strategy.
Are we speeding it down, slowing it up? What are we doing?
There's a lot of different parameters that we can control, but the basic ones are RPM. So how fast is that cut? How fast is the tool spinning? RPM. I did the wrong letter here. There we go. RPM. And then you have feed, which is how fast through the material the tool is going.
It's like the pressure of the tool against the material.
Yeah. So these two create chip load.
Load.
Yeah, and I'm going to try not to go too deep on the strategy thing, but if you imagine that tool that's let's do that same cross section again. So it's rotating this way through material, and if it's fed forward a certain amount as this happens, there is a fixed distance that controls the size of the chip of material removed.
Yep.
And
makes
so
perfect sense.
We optimize for that size. And in zirconia, it depends on the zirconia brand, what the optimal chip load is. So if you take too big of a chip, you'll make harder vibrations. And if you take a smaller chip, you'll make less vibrations, but there's diminishing returns. And so,
because if you slowed the feed way down, you could solve this, but now your mill time goes up, right?
Yeah. It's the world of trade-offs. And so these guys are big ones. Don't ever play with them unless you have calculated this. Um, I see customers using like an override in their software and turning the feed down. If you turn the feed down and you don't do RPM proportionally, you ruin chip load. So it should be done with intention, basically. And then quickly, the other ones that we have is we have step over and step down. So if we imagine this is the tool, it's cutting, and we're in a block of material like this, and this is the cut that I'm taking. I have step over, and then I have step down, and then what that's going to create is a cross section of material that's removed. And so you can increase or decrease either of those values, um, and you can control the load on the tool. How much energy is the tool seeing? And that directly affects vibration, directly affects surface finish. So yeah, there's a lot of balance to it. But really, it's not that complicated. I can sit down and probably teach somebody the basics in a couple hours.
Well, it's not that complicated to you because like you speak fluent Japanese when it comes to milling machines.
But I learned everything on YouTube, Rob.
Yeah. Oh my gosh. So
that's really not a joke. Yeah.
Any other images to look at?
Yeah, no, we do have quite a few, or a couple more. But one other thing, if your machine's not rigid, it's loose mechanically, you got wear, service ticket, start troubleshooting it. Okay, we'll try to go through a few more of these a little bit faster. Okay, roughing through finish. That's a pretty easy one to go through. So we see, so in a milling process, first you're roughing, you're using a big tool to do the mass reduction of the material, and then you follow it with a smaller tool to do the finishing.
Perfect sense.
And if you ever see, and I'm looking at these lines here. Let me grab the right tool. I'm looking at these. Ignore this. So a line that is horizontal and evenly spaced like this, if you're seeing that through your finish like this and like this, that is the roughing path showing through the finish path. And so if we have this is the surface of your crown, and then our roughing is going to come within a certain distance of that surface. So your roughing tool is going to stay away. It's going to do this. And it's making big, thick, aggressive passes, like a millimeter at a time. And then your finish tool comes through next, and it actually touches the unit, and it's much denser, right? So if your machine has a mechanical issue, or if the disc is moved during the milling, you can eliminate this clearance right here, and you're going to effectively shove your finish line out into where the roughing line is happening physically. So if you can imagine your disc is shifted very slightly, you'll show those roughing lines through your finish. So solves on this is make sure you've got rigid work holding, and you're loading your discs right. And then the other cause is machine wear, age, ball screws wear out, things wear out, and it gets sloppy and it can't repeat. So that's the bullet point on that one.
Yeah, it makes perfect sense. You're using a big, strong tool to get rid of lots of material quickly in a low definition type of strategy. But if that collides with the actual STL file that we're trying to reveal in this subtractive process, then your high definition tool isn't going to fix it. It's just that gouge is going to remain.
Yep. It's gone. It's gone below the level that the finishing tool's doing any work. So that's a quickie. Next one here, we'll look at gouging. So gouging.
Ugh.
Yeah, baby. So these images all have a this is a gouge. Oh, dang it. Pick the right tool, Greg. All right. We'll grab a different color here. So that's a gouge, that's a gouge. This is gouging. This entire surface is gouging.
It looks like the zirconia is like flaking off or something.
Yeah, it kind of does, right? But the mill made that mark. 100%
Wow.
it milled it. And you can even see, like on this one, you can see the layer lines from the finish crown. They're very dense. But the passes that finish tool took, you can see them in that image. And so this one shows up when the machine's doing 5-axis motion. So I haven't explained axes, but there's 3 axes that are moving in a line, and then in a 5-axis machine, then there's 2 axes that rotate, and they all have to be synchronized perfectly. And so what a gouge is it's when when the when the machine is trying to go in a, so this would be like the vertical axis of the machine, which would be Z, but we're going to go in and we're going to get an undercut. So we're going to actually approach the undercut from an off-axis direction. So this is your tool. So we've actually rotated one of those rotary axes to go in and hit the side of a crown. That's a 5-axis motion. And you get gouging when the machine is not rotating around the center of the disc. So you have a disc. It's got a perfect center from this way, and from the side view, there's a perfect center. And the machine has to rotate perfectly around that center. If it doesn't, then the tool, instead of hitting this surface perfectly, it will go past it and create a gouge. And so every one of these is actually from undercut machining. So there was a part of the program where the machine tried to do an undercut, often in embrasures, or like a lingual on a crazy long, anterior bridge, or a contact. There are undercuts, and the software is going to take the machine and do a 5-axis motion, but it's overshooting it because the machine is not rotating around 0. And so this one's a hard one to fix. Sometimes calibration clears it up, but usually it's send the machine in here and we precision align the mechanisms. So yeah, that's the rant on that one.
Wow. So that's okay. So the epicenter of orbit. I'm
Yep.
thinking planetary.
It is planetary. Yeah.
Is off, and so as it's rotating, it's like an oblong rotation, and
Yep.
so it goes into a 5-axis motion. It's off, and so then it just completely misses the mark.
Yeah. So the machine is traveling in an elliptical shape, like an oval egg shape, but the software is assuming it's moving in a circular shape because it should. And so the code is telling it move circular, but if it's not, it's moving elliptical, it's going to miss its mark, and overshoot it in most cases. So yeah, this one comes up, relatively often, but yeah, we send in an assembly and fix it. Okay, I think I've got one more, and then we can wrap it. Let's see. Equator lines.
Equator. Okay, I know what that means.
Yeah.
That's the junction of the 2 bulls that are coming together,
Yep.
right?
Yep. Literally the equator. And on a crown, because it's an organic shape, it's not a sphere. The equator is actually a curve. So if you're in the perspective of the machine and you look straight down on the disc, the edge of the crown is the equator. It's everything the machine can see from one side, and then everything it can see from the other side.
The northern hemisphere and the southern hemisphere.
Yeah, and so depending on the shape of the crown, that equator will follow the widest point of the crown.
Yeah, it's the height of contour.
Literally the height of contour. Yeah. So equator lines are lines that are the same all the way around the crown. They're not like thicker on one side than the other. And they perfectly follow the height of contour. So that's the definition of equator line.
And how do we fix those?
There's one cause, and it's mitigatable, fixable in some scenarios, but often it's like we mitigate it until it's workable. And these actually aren't as bad. I wanted to find some really bad ones, but they'll range. The thickness of the line can be like that, or it could be like, this, to where it's just cleaning off contacts. And so what causes this is, let me get one that's a little more. I want a line that has a white outline with it. So yeah, let's see. You got your crown. This is going to be another horrible Greg crown. And then we've got our tool, and I'm going to draw a tool and then use a trick here. Boom. This is my dynamic animation here. Okay, so my tool is working the top, and it's doing its finishing and everything. And it's all good until it comes down here. And when it gets to the height of contour, it transitions from the tip of the tool cutting to the side of the tool cutting.
Ooh, yeah.
And so that's why it appears in that area. Okay. So with that in mind, if we have our tool and it is doing the bounce dance, kind of like what we were talking about in the chatter slide, it's going like this. So it's actually in motion off of its center axis. And if this was a 1 millimeter tool and it's doing this, if you were to cut a slot in a piece of material, that slot would be 1 millimeter wide if it's not vibrating. But if it's vibrating side to side by, like, say 50 microns, then your resulting slot's going to be 1 millimeter plus diameter. So it's actually 100 microns. So it'd be 1.1 millimeters wide. And so what we get is we get a tool that's slapping against the side of the crown, and it just chews off the height of contour. And you get this.
Solve this.
Okay, we keep the tool from slapping the side of the crown. It's pretty simple. Okay, so why is it slapping? Most controllable thing for end user is collet maintenance. If they've never touched the collet or don't even know what a collet is, they're probably slapping crowns.
I've heard of the term collet from you, but I've forgotten already. So tell me, what is a collet?
Collet is the thing that holds the tool inside the machine. So it's the thing that grabs it. And
Not
if
the spindle.
So the collet's inside the spindle.
Got it.
If you've messed with hand pieces, it's like the chuck. So like if you take the chuck out of a hand piece, your burr goes in there. That's the collet. All milling machines have it. And if it's dirty, damaged, or not properly tightened, it won't hold the tool securely, and that tool wants to vibrate, right? And so if we're not holding it securely, it will slap the side of the crown. And so that's the number one thing. Number two thing, tool quality, geometry. Dull tools do this, it makes it worse. Bad tools do this, it makes it worse. So use a good sharp tool. And then material. I shared this with you not too long ago, Rob. Exactly the same file, like literally the exact same program for the machine. Same tool, same everything, same all controls, all variables controlled. The only thing changed is we went from a mechanical pressed, very inexpensive import zirconia to the harvest zirconia. And this defect disappeared in the harvest zirconia.
Interesting. So the quality, the density of the particles and all that can play into solving this problem.
It all circles back to energy in the cut and those vibrations. So because you've got a smoother cutting material, it doesn't make the vibrations because it doesn't resist the cut as much. And so like that actually was a huge eye opener to me about small particle size zirconia. Like, man, I was like, this is a great thing.
I think so.
Yeah. So yeah, that's all of it for now.
Do you have any optimized surfaces or surfaces that are brag worthy?
Yes. So I've got the images. There we go. I'm gonna get better at macro, Rob. I recognize it's not perfect, but I mean, kind of get the point.
The sprues are on there.
Yeah.
I love how we call them sprues, and they're actually what are they technically called? These are
connectors,
supports.
Supports. Depends on who you're talking to. Yeah.
And that surface finish is amazing.
So what I'll draw your attention to is the fact it's reflecting light. You see the little, reflections? You don't reflect light unless you've got a good surface. And this is off mill, untouched by a human. Um, and there is a little bit of a defect right here. This is where the machine's changing direction to go around the connector. Um, and that's another whole thing when it comes to optimization is like, let's avoid direction changes. The more you can do that, the better your result.
And that's cam strategy, direction
It's
changes.
it's cam strategy and it's nesting methodology.
Huh.
So I've actually become a fan of using multiple size connectors and then being very strategic on where I place them. Like I don't want to put a connector on the buckle aspect of a crown that I really care about, right?
Yeah, why?
Why? Yeah, don't do that. Don't put it on the contacts. And so, in fact, we've had pretty good luck doing single connector, one connector.
One
Which,
connector.
yep, even on a molar, yeah. Um, and some of the cam softwares can reduce the connector at the end of the program, so it's
So
thick
you're
and
milling,
sturdy while it's milling.
and you mill off the connector at the last step.
Yeah, yeah, and so that's kind of a creature comfort. There's a lot of stuff you can do on the software side, um, but yeah, this is what we want to be seeing is stuff like this, and back back for some contrast here. There's your contrast.
Yeah, it's like night and day, right?
Yeah, yeah.
So you can help people achieve this optimal result. Like this is what you do.
That's bread and butter. Um, People call us because they've got what's on the collage, and we do everything we can to give them what's in the other picture.
And the variables you're gonna talk about with someone are calibration, the collet, the spindle, the tools, the cam strategy, the type of zirconia. I mean, how many variables are at play here to optimize this outcome we're looking at?
A lot. And so usually like the typical case for us, we'll get something in that's horrendous, right? And then we'll get it. It may not get to this point, but it's going to get to freaking like way usable. They center it, and maybe some small defects get small enough for them to deal with it. And the reason that is because I can't control all the variables. All we're controlling is the machine itself. And labs want to make their own decisions on zirconia. They want to make their own decisions on tools, um, and strategy and all that stuff. And then you got the human element, which is a giant element.
Yeah.
And so the path to full optimization is a block of like 25 hours and willingness to change. Because usually it's not the time thing, but it's like the willingness to change. That's the big one. That's the hurdle.
Well, Greg, this has been very enlightening, super fun. I love
Yeah.
looking at problems to solve. You've definitely solved a whole bunch of problems in this one conversation, which maybe it's oversimplified a little bit, but man, this is really, really cool. Any parting thoughts? Like, how about this? Give me like the top 3 to 5 things someone should just check and look at on their own to, try to DIY and make sure their machine is working okay before they call you.
Yeah. Top is maintenance, specifically collet, followed by calibration. Second is your own process. Make sure that your humans are controlled. They're not making mistakes, loading stuff wrong or what have you. And then the third one is tools and material. You got to consider those things. And it's very tempting to use a $30, import tool. It is. I get it. But it's not really worth it in the long run. So yeah, that'd be the top three, and it goes way deeper from there.
I'm sure it does. Well, Greg, thank you so much for the time. Super enlightening. People can reach out to you at Denteon, and yeah, love having you
Yeah,
on here. Thanks for sharing
sweet.
your wisdom with us.
Anytime, Rob. Enjoy.